Good morning. It's 9 a.m. more or less, so thank you for coming. My name is Battista, as Mario said, and I come from this place here. Can you see the pointer? Maybe just me. Put a big one. Okay, so the university is placed here in the south of Sardinia, and we have a joint lab with the University of Genova, which is in the north part of Italy. We are more than 70 people, roughly 40, 50 in Cagliari, and the rest in Genova. And as you see, the lab covers different topics: AI security, AI for industry, biometrics, and cybersecurity. And I'm in charge of the AI security area, let's say, of research, where we do attack and defenses. We study AI security in the context of cybersecurity applications, and I will show some example to you. And also recently, we also started investigating large language models, vision language models, and so on. So just to start, I have a small question for you. So does anybody know when the area of adversarial machine learning or machine learning security started? Any rough ideas? Please shout one year that you think it started.
2014.
2014, okay. That's the wrong answer. But it was done on purpose, so thank you for saying that. So actually, it started 10 years before that. Okay, so if you Google for adversarial classification, there is a very old paper by Nilesh Dalvi and others that talks about how to bypass anti-spam filters. And then the field became more mature when in Berkeley, Blaine Nelson, Benjamin Rubinstein, and other people started to formalize the idea of attacking machine learning models. So they took threat modeling from cybersecurity, and they say, okay, what happens if we apply this to machine learning? Okay, and I will discuss a little bit of this later. And then, let's say, we contributed by basically formalizing attacks on machine learning models as optimization problems. We started from poisoning, and then we came up with a simpler idea of attacking models at test time. And up to 2013, 12-13, people knew how to attack linear models and nonlinear models, but nobody attacked deep learning models, okay? And then, meanwhile, if you look in 2012, there was the boom of deep learning with AlexNet winning the ImageNet competition, and then, of course, the very famous paper that popularized the area from Szegedy and Goodfellow, where they defined the notion of adversarial examples. But the idea of optimizing attacks as formalizing them as optimization problem and solving them with gradient descent or gradient ascent was much before that, okay? And if you're interested, I was giving a tutorial 6 or 7 times in conferences, but maybe you are too young for this, around 2014, 15, 16. And then after we wrote this survey paper where we tried to reconnect what was done in the AI security, cybersecurity space versus what has been rediscovered afterwards when attacking deep learning models. But the underlying strategies are the same. And I think they will follow the same rationale when it comes to attacking language models and more foundational models of today. So essentially, the underlying ideas are always the same. Okay? It changes the target, and it changes few tweaks in how you optimize the attacks. Okay, so just to focus a bit more on the historical parts, I want to tell you what happened, what was the state of the art around 2004, 2012. And essentially, people knew how to attack linear classifiers because they are very simple, right? And imagine that you have an anti-spam filter, which is running a linear model, which is pretty close to reality. Okay, so you have all of these anti-spam filters like Spam Assassin, BOGO filter, and the most popular ones. They all have a text classifier inside that is used to be a linear model, at least. And so this model seems to be simplified, but it's actually a good replicate of reality. So let's say you have a spam email, and you have a very simple representation for your vocabulary. So you just detect the presence or absence of words in the email according to the vocabulary or the dictionary that you built at training time. So let's say this is your dictionary that you see here, and in this email, the red words are those that belong both to the email and to the dictionary. Okay? So the feature representation of this email is just this Boolean vector X, where you have start, bank, portfolio, blah, blah, blah. Okay, then how do you compute the score of this email? You just do a scalar product. W are the weights that are learned by the filter. You just multiply them by the feature values, right? And then you sum up. So essentially here it boils down to summing up the weights of the words that are present in the email. So we just sum up these first weights that you see here, and you get 6. It's a positive value, so we say this email is classified as spam. Okay, now, let's say you are a spammer, and you want to bypass this filter knowing the weights. So we are in a white box case. You know the model. So what would you do? You can do 2 very simple things. One is you can try to guess the good words that are learned by the filter so that you try to decrease the score. So the main goal would be to take this 6 and decrease it up to the way that it becomes lower than 0, becomes negative. So what you can do is try to guess the good words of your model, like university and campus, and this is called good word insertion. Or you can try to misspell some of the bad words in a way that humans can still read them and understand them, but they are no longer detected by the filter. Okay? So just as an example, you can replace A with 4, and then you can still read start and bang, but those words are no longer detected by the feature extractor, right? So you bypass the preprocessing step if you want. And then you can try to add some good words, like here, campus. So now if you redo the computation, it will be -1. So it's very straightforward to bypass linear models because you have a clear connection between the feature values and the weights. So it's easy to know which features I should change to tweak the decision or flip the label of the classifier. But to give you an idea of the fact that it was not so easy to understand how to bypass nonlinear models, let me cite this paper from 2013, where the authors essentially were trying to detect computer viruses inside PDF files. So PDF files where you inject JavaScript code and things like that. You can analyze the structure of the PDF to detect whether there is a potential malware injected or not. And then they were using a classifier on top of this. What they did was basically they were able to bypass linear models, like linear support vector machines, but the attack that they designed was not able to bypass the nonlinear SVM. Okay? And so they conjectured that this was due to the complexity of the model. So the more complex the model is, the harder it is for the attacker to figure out how to attack it. And so complexity gives more security. That was the main claim. Okay? Of course, this is false, because normally complexity is the enemy of security, right? So if you have a very complex system, it's easier to find bugs in how it works. And then we had this idea of, again, formalizing the attacks as optimization problems. So as I told you before, the main idea is we want to decrease the score of the model on my specific input sample. So if you write it down, you can just write, okay, I want to minimize the score of the classifier, G, the output of my scalar product, on X plus delta, where delta is the changes I can do. So in the case of the email, it amounts to choosing which are the words that I should change, whether injecting them or removing them, trying to keep the same semantic meaning for the text. And this idea of keeping the semantic meaning in certain problems can be formalized as an LP distance in the feature space. Okay, like if you measure the AMIN distance or the L1 distance between the original email and the modified ones, and you say, I can only modify up to K words, this can be written down as a constraint in this form. Okay, so you impose a penalty on the norm of the perturbation, with epsilon being the number of words that you are entitled to change. Then in certain cases, you also have bounded feature spaces. This holds for the Boolean representation, but also for images, for instance. And then once you see this problem formalized, this is just a nonlinear optimization problem with some linear constraints in this case, if you use L1. And then you can basically use gradient descent to solve it if G is differentiable. And this is the case for many classifiers because you need them to be differentiable to train, to be able to train them. Like, so if you think of neural networks and SVMs with the differentiable kernels, then the function is differentiable. So you can just run gradient descent, optimizing with respect to the input. And this is mostly what you get. Okay, so if I'm looking for the minimum of this function, I want to shift this email or this sample from being classified as red, as malicious, for something that is classified as blue, so as benign. Okay, and I'm looking for the email that has the minimum score from the model. Okay, so it looks as much benign as possible, as more benign as possible. Okay, at that time there was no TensorFlow, no PyTorch, so we had to compute the gradients analytically by hand. Okay, there was no automated framework for doing that. This is just an example for neural nets and support vector machines. And then, of course, you can test these on images. So we tested these on the digits, on the usual MNIST digits, and you see for a problem that aims to classify 3 versus 7, so only 2 classes, let's say 3 is the bad stuff, like the spam emails, and I want to have this bad stuff classified as 7, which is the good class. Then if you run the attack, this is the, let's say, the first sample that is misclassified as a 7, okay? And surprisingly, what you see is that it doesn't resemble a 7 at all. It's still a 3 with some missing pixels and some pixels that have been added by the attack, okay? And this already shows that essentially, essentially few modifications are enough to bypass the model. You don't need to copy the target class. This is true in also many other cases. So what you need to do to bypass a model typically is to get far away enough from the source class. But you don't need to resemble the target class. So you can modify some text, and it doesn't have to look like a benign text. It's sufficient for this text to be different enough from the collection of malicious text or offensive comments that you may have collected. Okay, that's one thing that people always do not think deeply about, because we tend to think that the model learns what humans perceive. So it has to, you imagine that the end of the attack would be, I get something that really looks like a 7 or some other image. But in reality, you need to create something that is sufficiently different from your training data, in particular from the source class. Okay? Try to keep this in mind, because it's basically the essence of all these problems in machine learning security. And then, of course, we also tested, given that we wanted to attack the PDF malware detector that was claimed to be robust, we attacked it. And again, even if the PDF has a very different structure from text, what they developed as a malware detector was essentially, again, a text classifier. So they just counted these types of keywords that you find inside the PDF structure. So the PDF is defined as you see there. If you open it with a text editor, you see these keyword value pairs. And most of the detectors at that time were just based on counting the occurrences of some keywords, like how many pages you have, what's the type, what's the encoding used, and so on and so forth. Okay, so this is the representation. And of course, what you can do in this case, for example, without corrupting the PDF file, so you can still double-click it and it works, or it exploits your computer, and so the exploitation code still runs, is you can actually increase the number of keywords. So you can add pages, or you can add some other keywords like this without compromising the execution of the PDF. Okay, so in this case, my constraint is that the sample I modify has to have only X values that are higher than the source one. That's why I have this additional constraint here. Okay. And of course, if you run this attack, of course, it's a simulation. Then you would need to create the real PDF files. But this is, if you encode the constraints well, this is always doable. You see that in the case of the linear model, where you know exactly the classifier, you can bypass it. So this is the evasion rate, even by changing or injecting only 10 objects. The dashed line is what happens when you have imperfect knowledge. So you can train essentially a surrogate model, train on a different training set, trying to mimic the target classifier that you don't know. And you see that in this case, attacking the surrogate model yields also good success rate against the target one. Okay, so we say that the attack transfers to the target model. And you can see here that you can also break the nonlinear model. Okay, so the assumption that the nonlinear model was more secure was essentially not true. It costs a bit more, like I have to inject 20 keywords. But at the end of the day, I get 100% evasion rate. Okay, so it's still doable. Okay, that was before 2014. Then I'm sure you know about adversarial examples that were demonstrated against deep learning models by Zagedi and Goodfellow. But again, the idea is the same, right? You optimize some function. It can be the output of the model or the loss function, and you solve it by gradient descent. Okay, so whenever this logit difference becomes negative, you have found an adversarial example. And what was surprising here was to see that the perturbed image, so the adversarial example, actually looked very similar to the source image. And this happens because you have a very high dimensional input. You have a lot of pixels, so you can spread the noise across many pixels. So the more your classifier has parameters, or let's say the attacker is unbounded, has less bounds, the more you can add less noise. Okay? You can add smaller noise because you can spread it across different features. So ideally, if you have smaller systems that are more specialized, taking less inputs, then it's more difficult to craft the attacks. Okay? Okay, and again, how do they work? Here it's very simple. You pass the image through the network, and it predicts correctly a school bus. Then your loss function will be just be the difference between school bus and another output, let's say ostrich. You differentiate this difference of logits because I want to decrease the school bus probability and increase the ostrich probability. This gradient will just be an image. When you differentiate with respect to every pixel the loss function, it is scalar versus a matrix or a tensor, so you get the same size of the image, and then you just add it to the input and you iterate. After a few iterations, you get the sample misclassified. Okay? Now, this was just to cover the historical part, and then if you look at the number of papers, I took this screenshot yesterday from the page maintained by Nicola Scarlini, you see that the number of papers skyrocketed. Okay? So we had, I don't know, to 2025, more than 10,000 papers only in a single year. Still, there is no sign of flattening, but I hope at some point this will flatten out, maybe in favor of attacking foundation models and so on. But still, it's interesting to see that there is so much research on this and so small progress on really defending effectively against this threat. Okay, so possibly there will there be no defense that works against adversarial examples. And we will have to think on, instead of keep insisting on improving a single model to be more and more robust, maybe we have to start thinking about how to do a system-level defense. Okay, think more from a systems perspective rather than keeping hammering on the same model. All right, and I'm sure you've seen many, many examples of these attacks. People fabricated eyeglass frames to impersonate Hollywood celebrities. Or you can put stickers on traffic signs to have them misclassified. You can do the same with audio signals. And you can even do the same with language models. So you can add optimized prompt injections, or you can add these adversarial suffixes so that the prompt unlocks some response that the model shouldn't provide. All of this noise that you see here is, not, of course, not random. It's just optimized on purpose against the target model. So even those stickers that apparently seem in random places, they are optimized. They've been optimized against the model. Okay, so it's not random stuff. So what are the main challenges that I will try to dig deeper a bit in the remaining hour on security testing of these models? First of all, it's very difficult. When you do empirical evaluation, it's very difficult to get reliable numbers. So debugging and improving testing is still an open problem, especially if you move away from the LP norm models. And the other challenge is how to apply this kind of testing to other domains that are not just images or audio where you have additive perturbations. Okay, there are domains like malware or other cases where perturbations can be much more complex. So we'll try to give an overview of these. Meanwhile, if you have any questions, interrupt me anytime. I'm happy to take questions. I have more slides than required, so we can also focus on probably different topics as we go. And at the end, I will just give you the full deck of slides in case you are interested in investing or looking into different aspects, okay? But I'll see what I can cover. All right, so let's start from the security testing problems. So in the ideal world, what we would like to do, so this is like your input sample X, and you have your perturbation domain around it. Okay, so this green area is the maximum allowed perturbation. So you have to find, if you find an adversarial example, it has to be inside this green hypersphere, okay, assuming the L2. If you change the norm, it's the same. If you have L infinity, you have a hypercube and so on. But there is a domain where your perturbations are defined. This is the usual assumption when you formalize this problem. So you say, I have this epsilon is 8/255. If it's L infinity, it means that every pixel can change by plus minus 8. Okay, that's, of course, then this is arbitrary. But let's say you fix the perturbation size, and then this is what you get. So ideally, you would like to say that inside all of this volume, all of this domain, there's no intersection with any classification boundary. Okay, so that all the points that are inside this domain are classified consistently. Of course, this is very difficult to verify. There are certified methods that try to do this. But what they normally do is that they build upper bounds on this, on how this perturbation domain propagates through the network layers, and you get only essentially lower bounds on robustness. So you measure something that is much more pessimistic than what you have in reality. So you may find that a model is robust up to 40% against these perturbation sites and specific model, but in reality it could be robust 60 or 70. Okay, so you get a pessimistic estimate. And it's only doable in some simple and tractable cases. There are techniques for doing that and so on. So what most of the people do is measuring empirical robustness. Okay, so you run attacks, gradient-based attacks against your model, and you measure how many succeed and how many fail. Now, the problem is that if you find an adversarial example, you're sure that you found a bug in the model. Okay? But if you don't find any, you cannot conclude that there's no adversarial example in this domain, because I'm just sampling this volume in certain points, okay, according to the strategy that I have. So it's exactly the same as finding bugs in software. If your battery of tests doesn't reveal anything, it doesn't mean that you have no bugs in the code, right? So here is the same. So in the second case, what happens is that people overestimate robustness. So if I find that only 30% of my attacks succeed, robustness is estimated to be 70%, but in reality it could be much lower. Okay? And this is why in the research domain, we've had so many papers proposing defenses, the white dots here, and then they turned out to be broken. Okay? So the robustness values that were estimated for these defenses were overinflated because the evaluation was poor, was weakly done. So when you see the red crosses, it's about papers that show that the actual defenses published before were not effective. Okay? Under the same threat model, under the same condition, same optimization problem for the attacks, but they find better solutions, much more adversarial examples than they were evaluated on. And then even after some guidelines on how to do the evaluations were published, guess what happened? Well, that people just ignore it. Okay? They keep doing the same attacks, running for 10 iterations or whatever, and keep publishing defenses that were actually not robust, as shown in the end. Okay, so back in time, for example, one case of failure is what has been discovered to be obfuscated gradients. So you have a model, and the defense, what a defense does is essentially complicating the loss function, so that now you have a lot of local minima where your optimization, the attack optimization can get stuck into. Okay, so for example, if I start optimizing from here, I do gradient descent, I end up in this point. This point doesn't cross this horizontal line, so it's not classified as in a different class. Okay, but the attack process is just stuck very close to the initial point. Of course, these defenses, people that proposed that didn't realize this effect. Okay, they were just doing some complicated stuff, and at the end of the day, this was doing obfuscation of the gradients, noisy loss functions, but they were not aware of this fact. So Carlini and the other authors discovered this problem, and then essentially what you can do to break the model, to break the defense, is you can smooth this function. Okay? So you can sample around, for instance, and average, and this is already enough to smooth the loss landscape, and then run again the attack optimization that this time will work, and we'll find the successful adversarial examples. So what can we do to avoid this problem, this cat and mouse race, arms race, that people propose defenses, they are evaluated poorly, and then some other people have to come up with novel attack tricks to bypass them. So what do you do in software to prevent bugs when you develop software? Hopefully you do. You have a tool that does what?
We have like different types of tests, like unit test or like integration tests, and then we sort of try to have like a...
Yes, you have a bunch of tests, then you have this overall debugging process, right? But we don't have the same for adversarial evaluation. We just run the attacks as a black box. You keep the implementation from whatever library, you run it against your model, you publish the result. That's the worst thing you can do, okay? Because then someone will, probably Carlini, will break the defense. So back in time, we had this idea of categorizing all the known failures, which are those that you see here on top. I'm not discussing all of them. But for each failure, you can define an indicator. So you can try to detect whether the failure is present or not. Like if there is gradient obfuscation, yes or no, okay? Then if I detect the presence of obfuscation in gradients, then I can apply some mitigations, okay? So this is a kind of semi-automated process. I'll just focus on few failures in the upcoming slides. And you see here, so the first one we discussed was these stochastic gradients. So the gradient is noisy, is obfuscated. So if you run the attack as it is, you will follow the red path. And you see that the red path never crosses the horizontal line in 0. So this attack never finds an adversarial example because it keeps jumping back and forth, but it's not really minimizing the function. So what happens instead if you just sample around and average? Of course, it's more computationally costly, but at the end of the day, you find a meaningful descent direction. So if you look at the black path now, this is actually finding many adversarial examples along the path, okay? I'm just saying that I find an adversarial example when I cross 0 because it's the difference of logits, right? So it's positive when it's classified in the correct class, and it's negative when it goes in another class, okay? So when I cross this line, it becomes misclassified. So I find an adversarial example. This was one case of failure that was widely known. What was less known is that there are some libraries that have, let's say, a silly implementation error, if you want. So what the libraries do, and you see this was affecting many of these with a lot of stars on GitHub. So this was the state-of-the-art libraries used in many, many papers. What they do is they run some attack for some number of iterations, and then they return the last point, always the last point. Of course, this is a good strategy if the function is very smooth, so that at the end you end up in the local minimum and you keep staying over there, more or less. But if the function jumps a lot during the optimization, it's of course not a good strategy. So what happens in this case is that I start the optimization, I find an adversarial example in many iterations, but at the end, it keeps oscillating back and forth around the boundary, and the last point in this case is not adversarial. Okay, so it can happen that the attack returns a non-adversarial point, even if an adversarial example was found during the optimization. And this was another problem that we found in many libraries, and the patch is very easy to do. So what we did was to wrap the model that was attacked, track the attack queries, and then return the point with the minimum loss, rather than the last one. Okay, this is what you can do to patch it. And so then what we did was to reevaluate defenses that were known to be broken. Here you have the original evaluations, 58% robustness, 94 in this case, so this was bulletproof against attacks, 38, 35. Then you run the indicators. Some of the indicators are triggered. It means that there are failures in the evaluation. So now we need to apply the corresponding mitigations. First, we fix the implementation in the first. It means instead of returning the last point, we return the best one. And just by running the same setup, same attack that they run, the accuracy was already down by more than 20%. Okay? So they found 20% of samples that they did not report because they were not aware of this. And then if you also fix the the noisy loss problem, then you get basically 6% of robustness. And if you keep fixing it, it probably goes to 0. So there's no defense at all. Distillation, same story. So distillation was a very awkward case because what they did was to apply a softmax function at the outputs that was basically a step function. So if I differentiate the step function, I got 0 everywhere. So the attack is basically not even starting. So if you just unplug this softmax or change the temperature, then the attack runs very smooth. And then you can find the attacks very easily. So the notion here would be that if I want to increase robustness with these defenses, I should change the boundary of the model. Okay? So the boundary of the model should be pushed far away from the samples. You have to increase the input margin. That's the key to improve robustness, which is not easy to do in deep learning models. And all the other defenses that apply changes to losses or use something weird that do not move the boundary, conceptually, they're not doing anything. Distillation is just copying a model, a big model to a small model. Ideally, you have the same boundary. So why should it give more robustness? Okay? All right. And then we had just a flash on some recent papers we had. There was a paper published this year. It's called Attack Bench. So we took all the attack implementations available from all the different libraries that are out there. These totals more than 1,000 configurations that we ran with some computation, gently offered from Canada. Okay? And what happens is that then we ensemble all these results to build the most, let's say, the worst evaluation curve you can get. Okay? So these black lines here, these are obtained by ensembling all attacks. So for each sample, I take the best adversarial example and I build the oracle curve. And then we measure how far each attack is from this optimal, empirical optimal curve. This gives you a measure of optimality, we called it. And then you can rank attacks. So we rank the best ones and the worst ones. And again, surprisingly, if you look at the best performing attacks, and you look what people are still using to evaluate the defenses, especially in computer security conferences, they're still using very old, underperforming attacks, and not the newer ones that performs better. Okay? Just to give you a quick takeaway. So if you happen to work and devise a defense against adversarial examples in whatever domain, have a look maybe at what are the most functional attacks. And in this respect, I have to say that Auto-Attack and Robust Bench by Francesco Croce, they give a reliable assessment overall.
These are all done on white box models, right?
Oh, white box, yes. This is white box. Of course, you can also do the same on black box attacks, like using the same framework. You can, but again, you need just to run computation. Yes, yes. The success rate of the attack is a bit lower. It should be lower, except if you have obfuscation of gradients and so on. But it needs more computation because you probably need much more queries, much more forward queries. And then another small highlight is this paper where we published a sparse attack. So this is finding adversarial examples by changing the lowest number of pixels in the image. Okay? I'm not going with more details on this. If you're interested, we can talk offline. Okay, so now coming to other domains, of course, if you have images, it's fairly easy because you have this kind of model. So you add noise to image, right? So it's x plus delta. But if you have code, what does it mean to do x plus delta? Okay. So in some cases, you cannot just have additive perturbations with LP norm constraints, but you just have other types of manipulations that in general take an input, apply some changes, and give you hopefully a functional version of the input. Like if you take a malware or a code sample, you pass it through an obfuscator. This is a transformation that changes the code but keeps the functionality intact. Okay, just to give you an example. So now all of these transformations can be parameterized by theta, and the concept will be the same. I formalize an attack, and then I optimize it with respect to the parameters of my perturbation theta this time. So you don't have additive delta now, you have more generic models. For example, do I want to obfuscate certain types of calls, certain names of functions, so you can also have a guided obfuscation, for instance. So we analyzed this in the context of executable files for Windows. Why we did that? Because there was a point in time where people started using convolutional networks to classify malware samples, okay, Windows programs. to say this Windows program is good or this Windows program is bad. And okay, this is a paper that was published, so some co-authors were from NVIDIA. So now the connection should be clear, right? NVIDIA wants to sell GPUs, so if you show that you can classify malware with the GPU, then they are all happy, okay? Unfortunately, there was this problem of adversarial examples. So they published this paper and they say this is called malconf. So you take the bytes, it just learns from the raw bytes, maps the bytes to an embedding space like a language model, right? You take the words, the tokens, map them to an embedding, which is learned, and then from there on, you just apply whatever neural network you want to apply. In this case, they use some convolutional layers. All right, so they advertised this on Twitter when it used to work, before it became X. And they were saying, okay, this is good, interesting paper, blah, blah, blah. And I was pointing out this problem of the brittleness of these methods, so that if you slightly change the input, you can have the sample misclassified. And they were saying, no, this is modifying malware is not the same as modifying images. It's more difficult. You can break the code, blah, blah, blah. All these speculative arguments that do not hold, basically. So we just accepted the challenge and published a paper showing that this was basically broken very easily. Okay, it can be broken very easily. So what we did was just to take these executable files. The easiest thing you can do is pad bytes at the end. These bytes will be never executed, but they will be processed by this neural network. Just padding bytes at the end, okay? Now, if you pick the bytes at random, nothing really interesting happens. But if you optimize them, looking at the gradients of the model, you pick eventually only few carefully chosen bytes that are probably very indicative of benign behavior for the network. And then the evasion rate goes easily to 60% by adding 10 kilobytes of data over 1 megabyte or 2 megabytes. So it's basically nothing, okay? Now, you can say, yeah, it may be easy, however, to strip the bytes at the end. Yes, but you can find many spots in which you can inject bytes in the executable format that do not compromise its execution. Okay, I'm not giving the details of this, but all the colored areas that you see there, those are places where you can inject stuff that will never be executed, but it will be processed by the network. Okay, and it will be much more complex to understand what's not being executed at test time if you do only static analysis, as these networks do. And then, of course, here, now I have my manipulations. My manipulations will create space for a certain number of bytes. Now, how to choose these bytes is the problem of how I optimize the attack. Okay, so I use the optimizer to choose the bytes that I'm going to inject. So let's say I can inject 10 kilobytes. Then I tell the optimizer, suggest me the best bytes to be injected. And you can do this by gradient descent, and you can bypass many convolutional-like neural networks. Again, here there was another claim that some other people from another company said, yes, but malconf is trained on few data points, so it's vulnerable. We have networks that are trained on much more data. They are much more robust. False. Okay? You just run the attack, and they don't work in the same way as malconf. So you can bypass all of these. Or you can do also black box optimization. So if you cannot look at the gradients of the model, you can use genetic algorithms or whatever black box optimizer you want to query the model, and based on the outputs that you get, refine your perturbation, your set of manipulations. So basically, the optimizer will discover what works and what doesn't work. And you can do this in an efficient way, okay? Because if you run genetic algorithms as they are, they will take tons of queries. So what can we do to reduce the number of queries? We can use a strong heuristic. Okay, so we take, in this case, we took a bunch of benign programs from the Windows operating system, because we know that these samples are classified as benign, by definition, by the network, or by the model. So what we did was not to inject random bytes and refining the selection of the bytes, but just injecting chunks from these benign programs. And the optimizer has only to choose the fraction of bytes to be drawn from each sample. So in this case, we give a strong heuristic because we inject benign sequences, if you want, and we optimize over less variables because we take only 100 samples and we extract code from them. Okay, extract bytes. And that turns out to work pretty well. So injecting few kilobytes, again, can break not only neural network models, but also decision trees. Okay, so this Amber model is a gradient boost decision tree with crafted features. So you extract byte histograms, all these things, but again, it's still vulnerable to this type of attack. Okay? Remember, the decision trees are not differentiable, so we don't have a clear definition of gradient in this case. And what happens is that if I increase the number of queries, I can get the same evasion rate by decreasing the payload, the size of the payload. So as the attack runs more and more, you can find smaller and smaller payloads that still evade the model. Okay, so that's what you get if you increase the number of queries, smaller byte injection. Surprisingly, so after we optimized the attacks on this Amber model, we tested them also on VirusTotal, just one-shot transfer. Okay? And what happens is that many of these antiviruses were actually vulnerable to this attack. And it was quite surprising to see that, because we are not obfuscating anything. So the malicious instructions are still there, are still in clear, but just injecting, so like diluting this malicious content with some benign stuff is already enough to bypass many of these models. I cannot disclose what the first company is, but it is a company that claimed to use neural networks for malware detection, and I trust them, okay? Because we find that they are vulnerable to this type of attacks, so they're really using neural nets. We get in touch with them, provide the code and everything, but at the end of the day, they were not able to patch it. Because even if you do adversarial training many times, it doesn't work very well on these guys, on this attack that you dynamically optimize against it. Okay, and the same holds for Android malware detection. Here again, you can basically formalize this problem. The most famous approach, called Drebin, extrapolates all this content from the APK files and then maps them as a text classification problem. So you have 0 or 1 for the different features. For example, if an application has the permission to send a message, you will put 1 there, otherwise 0. If you can read messages, or if it calls certain APIs and blah, blah, blah. Okay, so all these commands, all these instructions are basically mapped to this feature space. I have a question, yes?
For example, in the CNN example, what happens if you, using this attack, you find like optimal text that's working and add it to the dataset and retrain the model, and then if you run again that checking of the optimal attacks, will it be still like good attacks or not?
Yes. So the thing is that this is called adversarial training. So you optimize the attacks against the model, you retrain the model on that. You can also do, I will show you in a minute, it's a min-max problem. Even if you solve that, in general, it gives you slightly more robustness, but not so much. So if you keep increasing a little bit the perturbation, you are from scratch. Okay? So it doesn't work really in practice, especially if you have high-dimensional inputs. Now, in the case of malware, it's 1 megabyte or 2 megabytes, which is even much more than ImageNet sites. Okay? So it's even more high-dimensional. So that's a problem. With text or language models, it's different, because text has a much lower dimensionality than this other type of data. Okay? If you think to a prompt, it could be a few kilobytes. It's not the same size of images or these huge files. Okay? So that can be hope for language models, I think, for text inputs. Okay, so I was talking about this. So Android essentially can be mapped again into a text classification problem, where you detect the presence or absence of certain API calls or permissions and so on, and then you can train whatever model you want on top. Again, here, some of these features can be removed, some of these features can be added. In general, all of them can be added. You can add fake permissions to send messages and so on, even then if the app doesn't use that. And then, again, you can try to see what happens if you attack these models and they are vulnerable, okay? By injecting 15 to 50 features in the white box case, you bypass detection completely. And if you have imperfect knowledge or black box, it's kind of similar. You just inject a bit more fake permissions or fake API calls. Now, the good news here is that you can get something better. Okay, so we were talking about the defense. This idea here is that the black part of this formula is what you normally do for training. Okay, so you minimize the loss function over some parameters W. If you consider the attack, inside the loop. That's what the inner maximization does. So the red part is adding this maximum over delta. So what the attacker does is trying to maximize the loss instead by perturbing the training points into a certain domain. Okay, so the black problem is depicted in the figure now. You have green versus red. You learn a model. That could be the result, right? If you add the attacker inside, it means that now the training points can be shifted around. This is normally called a robust optimization problem. Okay, so you want to learn something that is robust to shifts in the changes in the training data that are bounded by these domains. So what the attacker will do during the training iterations is to shift these points to maximize the loss. So the attacker is trying to evade the model that you just trained, okay, or that you are training. And then the classifier adjusts the boundary, and this iterates. Okay? Now you can study if there are conditions for equilibrium, if it's unique, and blah, blah, blah. Okay? There are formal methods to analyze this. But the good thing of this problem is that it has been shown that if the loss is linear, or it can be linearized, like in the case of the SVM, for instance, you can solve the max optimization in closed form. And this amounts to have a specific regularized problem, where the regularizer depends on the noise. Okay, so if you put L infinity here as your boxes on the points, then you will get a sparse model, L1. So it's always the dual norm. I find this very interesting because it connects regularization to something more concrete, right? To the noise that you can have on your data points. So depending on the type of noise you can have on your data points, there is a better regularizer that will improve robustness in this case, or even test accuracy, for instance. All right, so we can do this in the case of the Android malware. For the case of Android, we have L1 perturbations because we are injecting one permission or one API call at a time, and we want to have a minimum number of changes. And so we will use L infinity penalty here. Okay, so I will put some L infinity constraint on the weights of the SVM, like here. And then what you get is these red lines that are much more robust than the green line that we had before. Okay, this is the optimal response that you can have against this kind of attack. The blue one is obtained by ensembling different models. So I create some bagging or some boosting ensembles, aggregate the predictions, and I get some more robustness, but not by much, not that much. What works is really this other strategy. Why? Because in practice, putting a box on the weights means that every weight is now bounded to a maximum absolute value. Okay? So imagine that before you could have few weights that have a very large weight. If the attacker manipulates the corresponding feature, then it's enough to manipulate few features to bypass detection, right? But now if every weight has a smaller bound, then I need to modify much more features to get the same score decrease. Okay? Because if the weight is 0, 1, 0, 1, 0, 1, then I gain only 0, 1 in each feature. If one weight is 3, then I gain 3 by modifying a single feature. Okay, so that's why it works. And then we did some more work on other domains. I'm just giving some small overview of those. We did the same on, we tried to attack phishing web page detectors. So you have algorithms that can detect phishing web pages by looking at the HTML code. Again, what the attacker can do here is manipulate the HTML code in a way that the page is still rendered in the same way, but now the model sees something different. Okay? And essentially, you can bypass all of the academic detectors with few queries. Okay? This is, again, black box. So you can just query the detector multiple times, and at the end of the day, you can bypass it. And the optimizer chooses the type of manipulation that you have to do. And we also studied this in the context of web application firewalls. So now I have a website, and I have something that protects it from attacks, like SQL injection, cross-site scripting, whatever. One of the most popular firewalls in this domain is called mod security, and it uses the core rule set. I don't know if any of you is working on web security. You should be aware of these. It's basically a simple firewall. You have a bunch of rules that analyze the input query, HTTP, whatever, to your page, and then it flags some alerts, some potential attacks. Now, what these people that developed this mod security firewall from OWASP were not aware of is that it's basically a linear classifier. Okay, so they have a battery of simple signatures that apply to the input URL, and then these rules either trigger or not. So again, you have Boolean features if you want. So every one of these rules output either fires or not. And then they are assigned some called severity scores. Okay, this is just left to the designer of the rule. Okay, that it says, okay, if this is aimed to detect this special SQL injection, is very dangerous, so I give a weight of 5 or 7, maximum severity. Okay. Of course, what's the problem here? That these weights are not optimized on any training set. They are just decided by some domain experts without any clue on your data or on your traffic. Okay? So the first thing we did here was to show that basically if you train a model over these rules, then the firewall works already much better. And given that it's linear, you can also train something robust to the attacks. Okay? And this is one of the cases where doing this retraining or using these uniform weights gives you much more robustness because the attacker is much more constrained on the changes they can do on the URL. Let's say you have a SQL injection attack. There are not so many ways in which you can tweak the query to have the attack working. Okay, so keeping the functionality intact gives you more constraints, and then for the attacker it's much harder. And so here you have, if you look at the solid lines here, the red one is the basic performance of mod security on a certain data set. And all the lines up here, these are all different machine learning models. Okay, so it's very much more robust than before. And the dashed lines is what we obtain when we attack the models by manipulating the input query, the input URL. Okay? And you see that in this case, you still lose a bit, but not so much. So in this case, really, you can train something that works better and also have better robustness. Again, because the domain, the input domain is much lower dimensional than the other cases. All right. Okay, so these are all about attacks against models that are trained. Okay, so models that are already trained, and I'm trying to evade them at test time. But of course, it's not the only type of attack you can have. I was mentioning this paper on threat modeling at the beginning, and you can have it in a nutshell as it's depicted here. So depending on the goal, so whether the attacker is trying to break integrity, availability, or privacy of the system, you can have different types of attacks, and then you have to look at what the attacker can do. Can the attacker manipulate only the test data, or can they also access the training data? Okay, so if you reason in this sort of space, and then you can imagine that you have white box or black box for each category, you have these 6 categories of attacks, and you can try to categorize all of them, basically. So you have adversarial examples here. If I can manipulate test data and I want to undermine availability of the system to legitimate users, I can do sponge attacks. They try to consume energy and increase latency of the system. So the system becomes unavailable to the other users. That's the idea. Or you can try to do model extraction, model inversion, or membership inference for privacy. If the attacker can modify training data, they can backdoor the model if they want to violate integrity, because the model has still to work well for benign users, but when the attacker decides to step in, they have to get access, basically. So this is the idea of backdooring the model. Or you can do poisoning on the availability. So I want to inject some training points that screw up the overall learning process, and so on and so forth. On these, I will just quickly sketch these denial of service poisoning attacks. And then I think we can also cover quickly the last part. We still have a bit of time. Okay. All right, so let's say now that I want to craft this poisoning attack against a system. Okay, so you have a system that is trained on certain data points. And what you see here is the classification error on the test set. Okay? The test set is not plotted in the picture. What you have in the picture is only the training set. So classification error is measured on another test data sampled from the same distributions. In this case, they are just 2 Gaussians. Okay? All right, so now I just I don't want to find, to throw in some red and blue points to screw up the learning process at random. I want to find the best point that will increase the classification error. I'm playing the attacker role, of course. Okay? So for example, if you add a red point over here, what the SVM will do, will try to decrease the loss for this point, so the boundary will tilt a little bit towards the attack point at the cost of misclassifying some more of the benign points. Okay, so the classification error in this case will be 4%. The classification error, again, is measured on a separate test set, and of course, it's not including any attack point, okay, only benign points. All right, so the problem is, how do I find the best position for XC? Okay, this is just a random place. Of course, in 2D, you can look at the function. Okay, so I put XC in every possible location on a grid, train the model with the training data plus XC, and then measure the corresponding error on the test. If you do that, this is basically what you get. Okay, so when you see blue, adding XC doesn't change much, and when you see red, it's maximizing the error on the classification on the test set. So if you studied SVMs, right? Can you tell me why nothing happens when I look at this part of the plot? Anybody's? Exactly. So it's exactly. So I'm just adding what is called a reserve vector, that is basically not learned by the model at all. Okay. So it's classified correctly outside of the margin band, so it doesn't change anything in the training process. So that's why if I add a red point on this side, nothing happens. If I add a red point here, you see the error is even decreasing. Why is that? It's because if I add a red point here, the boundary becomes more vertical, right? And the vertical line was the optimal base classifier, the one with minimum error, because the two Gaussians the centroids are perfectly aligned on the horizontal axis. And then you see it's red here, because it's probably tilting and shifting a little bit towards the blue class, so it's misclassifying more samples in this region. Okay, this is actually one of the worst classifiers you can get with this problem, by just playing with 1 point. This is just to sketch the problem, okay, but now you have to write it down as a formal optimization problem, okay? And it turns out that this is a bi-level problem. Now bear with me for 1 minute, I will try to explain. So what you want to do, this is exactly the same as hyperparameter optimization, okay? You wanna, in this case, I want to maximize an error on a validation set made up of only clean points. And I want to maximize this error on my test set by changing XC. But XC is a training point. So it's like a hyperparameter of my classifier, like the regularization trade-off parameter, for instance. And so the inner problem here amounts to training the model, essentially. Okay, so I have to train the model every time by changing XC and measure the error on a separate test set. So this is a bi-level problem. There is a whole literature on how to solve it. It's not so easy. But basically, for this case, what you can do is replace the inner learning problem with the equilibrium condition, which is a linear system of equations, and then you can compute the gradient by inverting the KKT, okay? And this is a bit mathematically tricky, but conceptually it's not so difficult. So at the end of the day, you have found a direction that maximizes the loss on the validation set, okay? Assuming that the function is smooth enough, and so on and so forth. It's very unstable as a problem and very computationally demanding, so this attack doesn't scale to large data sets or more complex models, okay? Every time you do one iteration, you have to update the model to incorporate the new XC version. So every time you have to retrain the model. So it only works if it's incremental, basically. But it's very interesting to see what happens on the digits. Okay, again, we took two classes, 4 and 0, and you train the SVM. So if you train the SVM, even by flipping the label of this image, so I have 100 samples, I just take these 4 and change the label. And then I train the SVM. And the SVM is pretty much robust to this kind of random flips. So the error at the end of the day is still very small, less than 1%. But then if you optimize the attack, now you get this blurred digit image, which is 4 in the foreground, and there is a little bit of shade of a 0 in the background. And this is labeled as a 0. Then if you add this one to the training set, the error goes up to 20% on the test set. Okay, so just controlling 1%, I increase the error of 20% of my model. Essentially screws up the overall learning process. This happens because you have a linear model, and the loss is unbounded. So ideally, if you place a point, a training point, very far from the boundary, the loss of this point is going to be very, very high, and much higher than all the rest of the points. So the classifier will try to optimize to reduce the loss on this point, and you can basically control the boundary as you like. Okay? If it's a linear model with a point at infinity, for instance. So to avoid this, you have to go to non-convex losses and bound the loss or bound the feature space. And then there are other attacks. I'm sure you have heard about backdoor poisoning, so maybe I skip these, and I also skip membership inference because I think you have a lot of classes on privacy. But that's my take, more or less, on defenses. So what you see red is something that is difficult to defend against. Yellow is so-and-so. Green could be done under certain assumptions. Like you can probably defend against black box privacy attacks if you have a way to manage the number of queries that people can send to a system. If then they scale to a botnet or whatever, it's again complicated. And then, as the last exercise I did, I tried to map all these threats to the new generative AI landscape. Okay, so if you look at this, I tried to come up with the same taxonomy, but applied to generative models or language models. And most of these revolves around prompt injection and jailbreak now. So it's, again, this is the most investigated attacks, if you want, but there are other things you can do. Now, in the next few slides, I have some very broad overview of this type of attacks on prompt injection. And then some of the latest development we had. But I think, again, you will see much more detailed talks on this topic in the remainder of the school. So for black box, what people have been trying to do, of course, is have red teaming. So they have, let's say, people trying to bypass these models by changing the way they write prompts and so on and so forth. So you have data sets. And I found this very interesting toolbox from NVIDIA that tries to automate these red teaming attacks on models. This is called Garak. I don't know if you have seen it, but it may be worth a try. In terms of tricks, what people have been using is, for example, very curiously, encoding prompts. So first they tried using prompts in different languages, and then they tried to encode it with some base 64 or whatever type of encoding. Okay, and sometimes it works. Or you can do what is called a sandwich attack. So you can have a bunch of legitimate questions before and after the malicious prompt injection, and you put the malicious prompt injection in between, and sometimes it unlocks the response. Okay? Again, the notion is I put something that is maybe 80% legitimate with a small cherry on the cake, 20% malicious, and then the model answers. Okay, so it's always the same trick. But I think defenses on these are getting better and better. So I don't know how much it will last. And then there have been attempts to use LLMs in an offensive way, right? So instead of having people trying to reformulate the prompts and try to bypass the methods, you can also instruct LLMs to semi-automate this process. So there have been attacks in which the attacker LLM tries to reformulate the prompt to bypass detection, but this is really consuming a lot of queries, so people have tried to prune the prompts that are generated by the attacker LLMs to somehow get the attack more efficient. So that's really a broad overview. I have a bit more on white box. I think these are more interesting, especially this one. That was a paper published in, I think, 2000. It's a recent one, but it was the first one to basically apply the same idea of optimization of adversarial examples to language models. Okay, so what they did is essentially to change the loss function. So the loss function in this case is trying to force the model to answer something in an affirmative way. So like the usual example is the one of the bomb, right? So if you write, tell me how to build a bomb, the model is not replying. But if you try to force the model to generate, sure, here is how to build a bomb, or here are the instructions on how to build a bomb. So you can have this sequence, and you can force the model to generate this initial sequence. Okay, this gives you a loss function that you can optimize via gradient descent. And so you can keep your initial prompt and add this adversarial suffix at the end. You can add something that is meaningless, so this can be meaningless characters, and at the end of the day, this can unlock the response, or they used to unlock the response. Now, I think in most of the cases, this has been patched because the text that you add is really nonsense. Okay, so and this is easy to detect. So that was a very interesting first attempt. Then nowadays, there are some more refined or interesting attempts where, again, you are in a white box case. So what you can do is modify the input prompt, or you can also modify the weights of the model. Okay, and now there is all this bunch of research that is about model editing or representation engineering, where people have found that in the latent space of the model, concepts are categorized like in separate clusters. Okay, and there are directions in this space that categorize certain behaviors. For example, if you add one component during the generation process, you can make the response more, I don't know, lovable or hateful or less harmful, more harmful. So you can control the model as it's generating things. And there has been also attacks have been developed using this idea that you can, while the model is generating the output sequence, you can basically remove some directions from the latent space using this weight orthogonalization attack, and then you can unlock the response. Okay, so ideally, you can modify these weights in a way that the model answers to whatever prompt you provide. So it's an effective jailbreak technique. Okay? And it's very interesting. If you dig deeper in the mathematical formalization that they have, it's like doing, there are these spaces that are normally normalized on the unit balls, on the unit hypersphere. And what they do is removing, using a kind of Hausholder projection. So it's projecting a point like in a mirror. But what they do is they stop at the equator of the hypersphere. And then it's projected back. And this basically removes the prompt from the bad region. I know it's a bit blurry to visualize it, but it's very interesting to see how you can manipulate the representation to get this attack working. And so you can do many things on that. One ongoing work that we are doing is something similar, but what we would like to do, instead of forcing the model to generate a certain response that ideally we don't know, what we would like to do is look at the latent space of the model. And if you look at the latent space, you find normally, again, malicious prompts and good prompts, they are separate in this space. So the idea here would be exactly the same of adversarial examples. So you start from the malicious region, and I want to shift my prompt into the good region, okay, by manipulating the instructions or the prompt. Now, instead of optimizing this with gradient descent, that will normally give you meaningless suffixes to be appended, what we do is use another LLM to suggest synonyms to words that are in the prompt, and then we try to choose the synonym that mostly shifts the point to the good region. Okay, and this turns out to be very effective, and especially in bypassing perplexity-based filters. So these filters look at the text, and if it's not very likely, let's say, they can detect that it's something weird, okay, that has a high perplexity. So if you test all the previous attacks, like this one adding adversarial suffixes, or this SAA as a huge template where they have some adversarial suffixes at certain points. So instead of measuring the perplexity of the whole prompt, you have just a sliding window, and you measure the perplexity of this sliding window. Then you take the maximum or something similar, because I want to spot some adversarial suffix also inside a small portion of the prompt. If you do that, basically you can detect most of the known attacks. You see this is the detection rate, whereas the one that we're working on has slightly more perplexity than the base prompts that we're using. And so it's able to bypass perplexity-based filtering, while also being more effective in terms of success rate. All right, to sum up, I very much liked this paper, this position paper. I think it was ICML or something like that, where basically Javier Rando and Carlini and Tramer, what they did was to compare what was done in the case of adversarial machine learning before and after, let's say, attacks to language models. And it's very interesting because in the first case, we have like toy problems that are mathematically tractable, but still there's no effective solution after many years of attempts. Whereas on the other hand, the community seems to have approached the problem more with a cybersecurity angle rather than a formal approach that people from machine learning tend to have. So in this case, we don't care about how long the prompt is. There are no specific constraints on the attacker manipulations that people have studied. And so they just try to find something that breaks the model. And so it's really very much similar to what happens in cybersecurity to secure other traditional systems, like web security firewalls, web application firewalls, and so on. And I think in this case, the solution will come more, again, from a system perspective. So when instead of studying the model in isolation, especially now with agentic AI that you have a lot of tools connected together, it will come from a more comprehensive view of how these models interact, what permissions they have, who the model can talk to, which services it can access, and so on and so forth. And so that's, I think I can skip this one. And again, this was just about some kind of high-level compliance with the European AI Act, because in ELSA we just came up with this idea that we should integrate security and trustworthiness in the development cycles of machine learning, in these machine learning operations. But I will leave this to you for reference. I think I will also want to leave some time for questions. So thank you very much. I'm closing here. Yes?
So on slide number 63, you showed that there were some attacks on LLMs. So how do companies like OpenAI fix their model against these attacks?
Oh, this I have no idea. You have to ask OpenAI people. But I think in this case, I don't know if you can appreciate what is written here. Probably not. Let me see. But if you look at here, there are some weird characters, like this one. Then you have a dash symbol, then you have question mark. So it's text that is not really normal text, like not normal natural language, as we say. So if you measure perplexity on this, so perplexity measures basically how unlikely the text is. What's the probability of observing this sequence? Okay? These sequences are very unlikely. So perplexity of these sequences will be very high, and then basically you can spot that something is going wrong. Okay? That's one thing you can do. Then if you compare what people do in web security, they observe the input query and also the response. So you can also monitor the response as it's being produced, and if it's producing something harmful, then you can also block it. Okay? You can look at the latent spaces. So if in the latent space, I spot that something is going in a malicious region, where I know that the model will reply with malicious content, I can again block it. So you can have firewalls at different levels, input, output, and also looking at the internal representation of the model. That is telling you a lot. This is one line of defense. So I'm plugging something external to the model to monitor and detect. And you can also do alignment of the model. Right? So you can teach the model not to reply to these responses while you train it. As they do with reinforcement learning, human feedback, you can do something similar to avoid getting bad responses. But again, using only alignment in this case, I don't think will be a solution, because it's very difficult to control this type of models. Whereas I believe the solution will be built by different components. So you will have firewalls, you will have controlled interactions, you will have authentication, you will have all the standard measures that are in place normally to defend against this. I don't know if I replied to your question, but... And of course, we cannot anticipate all the attacks. Okay, so we can be as proactive as we want, trying to figure out novel attacks that will show up at test time and anticipate, so we can try to stay ahead of the attackers. But there is always a probability that is non-zero that someone else will find a way to break into the model, okay, or to unlock these responses. So another thing which is fundamental, and again, it comes from the cybersecurity mentality, is to have a short reaction time. So whenever I detect that something went wrong, I have to have systems to immediately patch the system. So I have also to have systems that are resilient. So the attacks may happen, because it will happen at some point, but you have to have a short feedback loop to just patch it as fast as you can. Okay? Yes?
Can we come up with a text that sounds quite natural, has a low perplexity? In other words, some kind of like, adversarial poem.
Yeah. Well, I don't know if you can do a poem, but the idea that we explored here was similar. So we just rephrase. So the first one doesn't reply, okay? The original prompt, you see Mistral is not replying. But then we replaced the initial prompt with some synonyms, and this unlocks the response.
And still it has low perplexity.
Yes.
So this method based on like measuring the
Yes.
perplexity will not work.
Yeah. So in this case, we didn't even optimize the prompt to have low perplexity, but you can also do that.
Yeah, exactly.
So you can have a loss function that wants to get the malicious response, plus a term that wants to keep the perplexity low to bypass the filters.
And maybe also the question, do you know how did they come up with this prompt? Because it's ChatGPT, it's closed source model. Like how did they arrive to this prompt like this?
Which one you mean? The original?
The previous one that they used for
I don't know.
breaking the ChatGPT.
So the original ones are just, I think they are attempts from humans to generate responses that are harmful. So you can have, there are different categories that talks about different things. And you can do the same on generative models that generate images. So you can try to generate harmful images, and these models have kind of bounds to protect them. But again, you can work on the text to unlock the bad content. Yeah.
Can you talk a bit more about how are you evaluating the latent jailbreaks? Are you just seeing the refusal rate, or also seeing like how specific the responses are? Because I assume like if you are replacing it with some synonyms, I mean this example it's very clear, but there might be cases where there would be like a little shift in the semantic meaning of the sentence, and the responses are not either specific enough or harmful enough.
Yeah. So this is again something that people should systematize better than what is done now. But the typical setting is that you have these data sets of jailbreaks, like the one in the orange box here. You send it to the model, and then you have a judge, which is another LLM, that tells you if the response of the model is harmful or not, and if it's aligned with the prompt, ideally. But again, it's another LLM, so it's not perfect. But again, there are many cases in which this is difficult to do, the evaluation, because you don't have a reliable ground truth. In security, again, there are tons of cases where you do analysis on websites and things that you cannot verify thousands and thousands of websites, but you can basically subsample and do a manual validation. So for example, here we could look at 10% of the prompts and see what the responses were, something like that. But it's more thoughts on how to scale these are at least as far as I know. Maybe some other speakers have better ideas, but it's not easy.
I think, so I want to know about the latent jailbreak that jailbreak that you have mentioned. So you were replacing the words with synonym. So is there any heuristics, do you do it for every word, or like this specific word that you're targeting? Because what I'm asking is that for some of the words that have recently in this line, for instance, I think adversarial prompter, which also tries to do something similar. I think they want to also maintain low perplexity. The number of optimization steps that are required to get to the final jailbreaking prompt is significantly more. And I'm assuming that if it is heuristic, it will be less than that. So I think
Yeah. So I think what we did here was we generate 10 potential synonyms for a bunch of words, and then we query the model every time 10 times, but it's just a forward query up to the latent space to see which one is shifting more towards the benign region. So it's a bit query expensive up to now, but I'm sure there is a lot of attempts you can do to save some queries. We tried also looking at the gradients by backpropagating the distance function, but then it's very difficult to select the synonym by looking at the gradient direction. That's more challenging. But again, this is something one could better investigate. It's exactly the same we did for the malware case when we have to select the bytes. We backprop the gradient up to the embedding space, and then you have to use some discrete projection, and you can use many different criteria. But maybe you find one that works also here to save more queries.
One probably follow-up to that. So if we take this into like a LLM versus LLM case where LLM is like making them like the adversarial prompts, do you think that if we use a LLM of a lower capacity, for instance, like with one with a less parameters, do you think that will be more successful against, let's say, bigger model?
I don't know. This one, I think the synonyms were generated with a powerful LLM here. So if you use something weaker, I think it's going to work worse. But we should test that as well. Any other questions? Yes.
In this year's ICLR, there was a paper about certifying models, particularly with respect to uncertainty calibration, and they argued that there are attacks possible that really don't impact the accuracy in any way, but they only target the prior score in such a way that you can detect it only if you focus on the calibration. Does your published attack bench also include such attacks, or?
No. We just tested the ones that aim to have misclassifications. For uncertainty, we did another paper that was exactly attacking the uncertainty estimate of the model. And we've been studying this also in the segmentation problems, image segmentation. So you can basically have the same classification or the same segmentation, but a completely different uncertainty map on the image. Again, whatever quantity or metric you're using, by modifying the input, you can basically tweak it as you like if the model is undefended.
Do you think that can be a way to defend, I guess, adversarial attack, making them more difficult to trust, computationally speaking? Right?
Yeah, this was something we debated in a DAGSTOOL seminar some time ago. But at the end of the day, I don't think it's a way to go. Because if it's gradient-based, it's still very efficient. Maybe for language model, you need larger memory. But I don't see, it could be, I see the argument coming from the cryptography space, right? That if you increase the computational barrier for the attacker, then it becomes harder, because then you can change your password more frequently than the attacker can brute force it. But here is not the same, unless, I don't know, this should be studied more empirically, I think. Like, if you change your machine learning model or you update it faster than the attacker is able to discover something about it, probably in this case, something can be done. But the problem with machine learning is also that you need the model not to be so different from the previous one for compatibility, retrocompatibility with your systems, and then the attacks transfer with high probability, so it's not like changing the password. It's like changing one character of the password, maybe. And then, I don't know, in my view, I'm a bit pessimistic about this. But
in this regard, what do you think about open sourcing large language models? It sounds like you believe there's no proper defense against breaking such models, and then an inherent security threat if like companies or universities open source large language models.
So it's a bit, so I'm not saying, for language models, I do see more space to improve, because again, text enables, so even if you look at the perplexity metrics, especially if you kind of bound the length of the prompt in some way, then I don't think that the attacker has so much space to unlock the responses. Okay, so I'm more positive on defending attacks that are crafted on text rather than images or higher dimensional inputs. Okay, that's one point. In terms of open versus closed source, there is the usual argument which is security by obscurity or security by design, right? And we shouldn't rely on security by obscurity in general. It can be an additional measure, but normally if you want to have real security, it should be security by design. So in this case, opening weights, because it's not open source, it's open weights. Maybe helps people coming up with creative ideas on how to improve the defense levels and so on. And then you can have a part which is closed. So maybe your firewalls, your detectors, whatever OpenAI is doing, is closed source. And they have quite good defensive mechanisms on these. But for the rest, it's also helpful to, I think it's even in their business models. Like if you think what Meta is doing, they open source PyTorch, they open source models, whatever, because then they can grasp ideas from the community and incorporate them in their products like very easily. Okay? And even if you come up with some ideas that reduce energy consumption by 0.1%, for them it will be a lot of money if you scale it right to all the production system they have. So that's the business model that they have. And then I think, of course, certain parts are closed and they only know what they're doing. So I think that's the right model. That's the right trade-off for managing these security aspects. Still, we are deploying, not we, but these companies are deploying tools at a very fast pace, and security is often an afterthought, not to slow down the business process. So with this, we have to be careful, because at the beginning, they will probably be very vulnerable. Right? It's like when you update your computer with the day after they release the system update, then something goes wrong for sure. So normally what I do is I update after 6 or 7 months, the operating system, okay, just to give you some thoughts. Okay, anyone else? No, if not, thank you very much, and looking forward to the coffee break, right?